In this next section of our chapter on gases, we're going to be talking about an underlying theory that explains many of the observations that we see regarding the ideal gas law, Charles's law, Boyle's law, all the other laws that led to the ideal gas law. And this theory that underlies this is kinetic molecular theory. We've already sort of alluded to this, but the idea here, many of these observations about gases were made before we had a theory of atoms and molecules. And so they just knew these things about pressure and volume and temperature, but had no concept of the idea of number of moles or what a gas actually was. And so kinetic molecular theory was developed later and explains many of the observations that we observe about gases. So the fundamental idea of kinetic molecular theory is that gases are a bunch of particles, represented with little circles here, and they are in random motion. So they're moving around, and there's a few assumptions that go into kinetic molecular theory. So these are moving around randomly, they're colliding with the walls, and that's what generates pressure, and they have a particular speed, a range of speeds. They're not all moving at the same speed. Okay, so what are some of the assumptions that underlie kinetic molecular theory? Well, one assumption is that the gas particles are very, very small, which is a really good assumption. Are small, and you can neglect the space they take up. So this is one assumption of kinetic molecular theory, that these particles, we can treat them as if they're masses, but they have no volume. Because these are atoms and molecules. They are very, very small. And at sort of atmospheric pressure, sort of regular pressures, they are spaced so far apart that they basically act as if they have no, they take up no space. All right, so that's one of our assumptions. One of the other assumptions of kinetic molecular theory is that we have constant random motion. So there's no the particles are just moving randomly about. There's no directionality to them. They just go in a straight line, whatever direction they're going, until they hit something. So they either hit another gas particle or they hit the wall of the container that they're in. So that's one of the assumptions that we make. Assumption number 3 is that the average kinetic energy of the gases depends only on temperature. So the hotter a gas sample gets, the faster the things will move. The colder it gets, the slower they'll move. And it's specifically not the speed, but the average kinetic energy. This will be relevant later when we compare speeds of different gases. Gases don't move at the same speed, or same average speed, depending on what gas they are and how heavy they are. But the kinetic energy is the same for all different kinds of gases, which leads to the fact that many of the properties, or all the properties that we observe, are the same for different gases. All right, so average kinetic energy only depends on temperature. Assumption number 4 is that we have elastic collisions. Now let's go ahead and break down what this means. Elastic just means no energy is lost when they bump into to things. So when a gas particle hits another gas particle, there's no loss of energy. This is kind of like assuming they're all little bowling balls or hard spheres where they just bounce off of each other, instead of something soft and squishy where if they hit, it sort of absorbs the impact a little bit. We make the assumption that that's not what's happening. No energy is lost as they bump into the sides of the chamber or into each other. And our final, and another really important assumption, is that there are no forces between the gas molecules, or the gas particles. So this is basically saying that if you have two gas particles kind of nearby each other, they're not going to pull on each other. There's no force between them. Now, this isn't 100% true, and we'll see that when we do get deviations from the ideal gas law, this is one of the reasons why, is that there are actually forces between the molecules. But because the gas particles are so far apart, and these forces tend to be quite weak, they really don't matter at sort of regular temperatures and pressures. But when we compress the gas, when we push it together a lot, that's when it's going to start sticking together and forming liquids. So when we get close to a gas becoming a liquid, when it gets close to being condensing, whether because of temperature or pressure, this assumption will start to break down. But for most gases, this is a very good assumption. There's no attractive forces or repulsive forces. There's no forces between the gas particles. All right, so these are the fundamental sort of underlying assumptions behind kinetic molecular theory. And in the next video, we'll look into how this translates into the observations we see with the ideal gas law.